Okay, good evening. This video is a continuation of the last video, and we still in the topic of top bars. Last video, we compute the shearing stress or the actual shears for this triangle, this one. We compute that, and this is from, if you remember, this is x, which is 8. That is the this triangle actually is this one. We finished that last video, and now we will go into consider this triangle for the top bar also. This triangle. Okay. Let us, that is at the left of the B. The triangle just left of the B. So this triangle is this one. And the shear, maximum shear is 100 kilonewton. So the critical shear is the distance from this one, the distance. So solving that critical shear, 100 minus 20 times 0.57. 20, if you remember, this is the W, the load, and this is D, effective diff. And computing this will give us the 88.60 kilonewton. That is the shear critical. This one, shear critical here. And the actual shear is computed with this. B critical divided by the BD. Substituting the values, we have this. And computing that, we have 0.4860. This is the actual shearing stress. And the allowable is this one, 0.4166. The actual is greater than the allowable. So therefore, we have to provide a stirrup to support that axis of shearing stress, axis over the allowable. So we have to provide stirrup. Computing the spacing of the stirrup, our stirrup is this one. Using the number 10 steel bar. So the spacing of that stirrup is equal to AB, FB, B actual minus B allowable, then times the base. The total, this AV is the total cross-sectional area of the legs of the stirrup. This one, total. Whatever the cross-sectional area of this times 2, because there are two legs. And since we use the number 10 is the cross-sectional area is 100. So it is 200. Because we have two legs. We have two legs. Number 10 has an cross-sectional area of 100. So 100 times 2 is 200. The FB is the specified tensile strength of this steel bar, which is 140. And the actual shear minus the allowable times 320, the base, will give us 1261.0, say 1260 millimeter. We will compute the maximum spacing. Maximum spacing is less than or equal d over 2, d divided by 2, or 600. D is the depth of the section. 570 divided by 2 is 285 millimeter. So we adapt this one because this is a very big. So this we will adapt this. Equals 285 millimeter. That is the spacing of the stirrup. Okay, therefore we use the stirrup number 10 at 0.285 meter on center, or meter center to center. So that is now our stirrup. Next is to compute the number of stirrups. Number of stirrup. This triangle is actually this one. We have two triangle here. This triangle and this line is parallel to this, or offset of this line, parallel of this one. Our shear here, maximum shear here is 100 times 10 to the third over BD. Computing that will give us 0.55. Okay, this is the maximum shear, 0.55. And the critical force shear is this one. This is the actual critical shear, 0.486, and this one the allowable, 0.4166. Okay. The height of this big triangle now is 0.55. This one, 0.55. That is the maximum shear. This height from here up to here. And the height of this small triangle from here up to here is 0.55 minus the allowable. This one, 0.4166. Will give us 0.1344. So that's the time we will going to solve the total length where the stirrup are needed. Okay, we have the value of these two triangles. To solve the total length where the stirrup are needed, we have to take the ratio between the small and the large triangles. So L prime, this L prime divided by its height, 0.1344, this one is equal to the ratio of the big triangle. 5 from here is 5 divided by its height, 0.55. So therefore L will give us 1.2130 meters. So LT now is 1.2130 plus 0.50 55. $57 because this is the D. This is D. Okay. Will give us 1.7830 meters. So number of stirrups is equal to this length divided by the spacing of the stirrup. This one will give us 6.26. Say 7. So the stirrup that we have need for the total length is 7 stirrups. Okay. It's come out that the number of stirrup is 7. 7 stirrup of number 10 at spacing of 0.285 meter on center. So this is the detail. Our stirrup here is this one, 7. 1, 2, 3, 4, 5, 6, 7. And this is space at 0.285 meter on center. This stirrup is well placed or installed begin at spacing over 2 from the face of the support. From the face of the column, for example, this is the column. This is the column. Our stirrup is begin here, not here, which is measured S over 2. S over 2. Meaning whatever the spacing is divided by 2. And you measure it from the face of the support. So you place or put the first stirrup. Then the other one will be follows at 0.285 meter on center. That is the stirrup. Begins about 1/2 of the spacing from the face of the support. And this top bar is 2 of number 25 and 1 of number 20. Okay, the bar here is 2 of number 25, meaning only 2 top bar here. And this is 3 bars. And this is the bottom bar, 8 of number 20. So that is the placing of the stirrup and the reinforcing bars. For this section, we will start here. This is the base, 320. We have 8 steel bar here. 1, 2, 3, 4, 5, 6, 7, 8. The center of this bar is in the middle, this one. So from here, that is the effective depth of the beam, 570. That's why we have that. And the between the two layers of the bar is computed to 25. That is the this one spacing plus the diameter of the steel bar. 1/2 diameter of this, 1/2 of diameter of this is equals 1, which is 19.5. So we have this one, and say 50. As I said, the spacing of this one, the two layers of bar is 25, this one, plus 19.5. 1/2 of the diameter, 1/2 of the diameter of the bar become 1, which is 19.5. Okay, this is the result, say 50 millimeter. For this center of the bar to the bottom of the beam, we have 40. 40 is this one. And the 11.30 is the diameter of the stirrup, plus 1/2 of the diameter of the bar, reinforcing bar, which is 19.5 divided by 2 will give us 6.05, say 65 millimeter. And the distance of the center of the two layer bars to the bottom of the beam is 50, because this is 50. The distance of this is 50. This one, 50. Divided by 2 plus 65. Plus 65, this one. So will give us 90. This is 90. For the top bar, this is 90. So this is also 90 here. And from here to the bottom of the beam, that is 570. The base is 320. All in all, the dimension, the vertical dimension of the beam is 660. 660. 90 plus 570, 660. So, actually, this is the specification. All of this will be based on this computation. Where the A here, this one A is the maximum size of the coarse aggregate, which is 20 millimeter. Okay, let us check for the one layers. If we will going to place the bottom bar in one layer, we will check what happening. What will happen? This is the section. Let us B prime. 40. 40 here is the concrete covering. Times 2, because both side. Times 2. Plus 11.30, that is the diameter of the number 10 bar. Times 2, because 2 legs. That's why. Then 8 reinforcing bar. 1, 2, 3, 4, 5, 6, 7, 8. Times the diameter 19.50. Then plus the spacing. Here, the spacing. spacing is 26.70, which is 7. 1, 2, 3, 4, 5, 6, 7. 7. And computing that will give us 325.50 millimeter, which is greater than the base of the section, 320 millimeter. So failure. So therefore, we use the 2 layers of the steel bar. So that is the end of the singly reinforced WSD method. And inshallah, the next video, we will start the singly reinforced USD method. Up to here only this night. Have a night and good sleep.